right, let's get talking about bending and still beams. So some examples of some failure modes. It's not the easiest to see in here, but you can see where this flange rippled. That's a local buckling failure. I've added a couple videos for your viewing pleasure. If you go to the PowerPoint, you'll be able to pull those or have a link direct, or you can go to there. Let's see if that brings that up. Okay, anyway, this is kind of a sense of the video. It shows you a lateral torsional buckling failure mode, which we'll talk about it a little bit more here in a sec. Okay, so some of the fundamental mechanics of bending, if we have a simple support, point load in the middle, as the beam deforms, the top goes into compression. You can see how these circles are getting squished. And on the bottom, it goes into tension. You can see the circles are getting elongated. When we have a multi-span beam, the same thing happens in the middle, but over the supports, the opposite happens. The bottom goes into compression. You can see these circles have gotten smaller, and at the top, they go into tension. Looking at the general behavior, if we have simple span beam, again, compression stress at the top, tension at the bottom, and it varies linearly from face to face or top and bottom. Opposite is true in a cantilever, where we have tension at the top, compression at the bottom. And then this kind of expands on that, different places along the length of the beam, different stress states. And one of the things that I've added here is the yielding that we assume takes place in LRFD design. So ordinarily we're used to thinking of stress as linear. In LRFD, we say everything yields. So at some point, the cross section is fully plastic, and then out away from the maximum moment, it may be that linear variation before things have yielded. Okay, one of the most important things about steel beams is to understand the fact that they tend to roll over due to lateral torsional buckling. So if I have a thin beam like this channel and it's loaded, if the span is long enough compared to the section properties, that beam will tend to roll over. Here's another picture of that: unloaded, light load, moderate load, and then quite a bit of load is causing this thin strip of plywood to roll over. And you saw that clip, that snip of a video earlier that had some of that going on. So take a good look at that. That's kind of at the crux of steel design, is understanding that this phenomenon happens. So we have three ranges of behavior. One is yielding, where things are sufficiently braced that the whole cross section can activate. The second is where we have elastic torsional buckling. So if it's super slender, that thing will roll over. And when you take the load off, it'll actually go back to its original shape. And then we have an inelastic torsional buckling range, where if you did buckle laterally, some of it would be permanent deformation due to the yielding of the material. When we brace beams, it's important to understand we're not looking to limit lateral displacement, we're looking to limit twist. And there's some different types of bracing here that you can look at. All of them basically reduce the unbraced length of the beam. Okay, so I'll let you get into that more. The code has some requirements for bracing forces and stiffness, so you can use these equations when you're designing the bracing. Generally, those forces tend to be pretty low. So let's say we had a connection between a beam and a wide flange, or even a joist and a wide flange. Those tend to be plenty strong to brace the member. But if you don't know, check it and get to the point where you have some comfort with it. Okay, deflection often controls for steel design. So rather than starting with strength, it's helpful to start with deflection. So sizing, you can start with a deflection equation, rearrange and solve for the moment of inertia required. And that may be your best place to start when sizing a beam. Here's those equations, this derivation here done for a uniform beam and a point load with different deflection criteria. So if you follow these units, follow these equations, you can solve directly for the moment of inertia that you want for one of these members. All right, deflection limits. Here's some criteria from the IBC. This is a good place to start. Talking to the owner, understanding the building use may change these. Equipment, usually we're in the L over 400 plus. Definitely want to check with the manufacturer as to what they require. Sometimes they'll give you a number, sometimes they'll look at you like you're crazy. This slide gives you the actual deflection based on, or the allowable deflection based on different criteria and spans. Just a helpful table. You can calc it all out by hand yourself, though, if you like. All right, for vibration, we go to AISC Design Guide 11. I'm not going to get into it here much. It's good to check this for office floors, especially when you're getting into open web joists as the floors rather than wide flange beams. Okay, so let's look at the limit states. We talked about this figure where you have a plastic behavior, inelastic, and then fully elastic. So let's see here. Base equation. Okay, so the base equation is nominal moment strength is equal to Fy, yield strength, times Z, which is the plastic section modulus. You get that out of the manual in the tables. And that's this area right here. This next area is given by this not so simple equation. What you'll find though is it can be broken down piece by piece and you kind of chew your way through it. It basically has that plastic moment term, a elastic moment term, and then some ratios between LP, LR, and your LB, which your LB is your physical brace length. LP and LR relate to the behavior of the section. So you choose LB and then you calculate LP and LR. And those equations are given here. Not so enjoyable. But there is a table right here where LP and LR are calculated, so table 3-2 out of the manual, where you can just come here, choose your member, and get those directly. So anyway, that's that. And then if you are in this elastic range, which generally we try to stay out of there, but sometimes we end up there, the equation is a critical buckling stress times the elastic section modulus, and this critical buckling stress is given by that equation right there. Okay, so we talked a little bit about the properties. So this CB, let's see here. I always get confused because I use this so rarely. Oh, CB is your moment ratio. Your J and C would come from here in that equation. Okay. All right, we talked about this table a little bit. This is nice. Let's say for this 18 by 35, it gives you the plastic section modulus, the bending strength when it's fully plastic, which corresponds to this point, bending strength at R, which is this, in this case, 12.5 feet, which corresponds to this point, and then moment of inertia, and then some shear values, capacity values. This is a great beam selection table. We also find in the manual these charts where, based on unbraced length, so let's say I'm a 14-foot unbraced length, I'm a 21 by 11, I have 975 kip feet of capacity. So these are nice for beams where we don't know, where we know we're off of here, we're somewhere along here, but rather than calculating all these long equations, we can just come to these figures and find our values. Generally what happens is we come in here with an unbraced length, a moment that's on our beam, and then we can choose a beam based on whatever makes the most sense. Okay, design steps, you can get into that. Some example drawings here, different types of framing, different types of connections. Here's a shear connection, here's a moment connection. You can see the difference from the point of view of cost and effort, and that's that. Couple more things, or one more thing, I've got a beam design example, so this should walk you through a lot of the nuances of what I just talked about. All right, good luck on your quiz. We'll talk more in class.